Hi, so I'd like to welcome everyone to this course. This course is, my name is David Henty. I'm in charge of training at EPCC, although the ARCHER2 training program is actually organized by my colleague, Juan Herrera, but he's not available today. This course is part of our ARCHER2 service. It's also part of our PRACE training center, a big European project we're part of to deliver HPC training. And the course will take place on ARCHER2. Hopefully you'll have applied for an account if you want to do the practicals. But the course is actually delivered by the developers, experts on Scalasca, Brian and Christian, who you'll see in the window there. So I'm very glad they're able to give this course. EPC just sort of facilitates it. And we've done it regularly, for quite a few years actually, as a regular event on ARCHER2. So there will be there were a few of us from EPCC, at least 3 of us from EPCC on the course. I can see my colleagues Gavin and Mark here. So, I mean, in the first practical session, there may be issues with logging on to ARCHER2. It's slightly quirky getting on because of extra security restrictions we had to put in about a year ago, like a lot of people. So there are maybe one extra password that you didn't expect. But we can guide you through that if there are any issues. And we have quite a bit of time. The course is today and tomorrow, so we've got plenty of time to get people up and running. So I'll just pass over now to Brian.
Okay, so hopefully you can hear me, and hopefully I can get some sort of slides onto the screen, which was working before. This was what was working before. Sharing. Hopefully you're seeing my introductory slide.
Yeah, looks good.
Okay.
Yeah, I can see it fine.
So yeah, I mean, Christian and myself are both from Jülich Supercomputing Center in Germany. That's one of the top tier systems in Germany and the PRACE framework in Europe. But we're happy to be here with you virtually at EPCC, giving a course on the ARCHER system, which is one of the main systems in the UK. So we have the event arranged for you online today and tomorrow. The morning sessions will be presenting the tools, demonstrating them on ARCHER2. We're going through some small examples that we have prepared and allow you to see how the tools are used. We'll probably try and do them at a slow enough pace that those of you who are on top of your game can follow things with the provided exercise. If not, then you can come back and go through the slides at your leisure in the afternoon session when we can come back to help you with the slides, help you with using the tools. And ideally, some of you will have your own codes that you build and run on ARCHER, and we can apply the tools to those as well. Today, we'll be going through the profiling part of things, and then in the afternoon session and tomorrow's session, we'll be moving on to tracing, trace collection, trace analysis, giving you a little bit more insight, a little bit different perspective on the performance information. So that's the outline. I think there's a lot of flexibility in terms of when we have breaks. We'll try and keep to a reasonable schedule for having a break and then stopping it for lunch. So the target here is, as it says, 12:30 British time, 1:30 for the others who are in Europe with Christian and myself, and then an hour break for lunch coming back after that. I'm going to stop sharing for a moment because I heard lots of beeping and things going on. So I'm curious what was going on there.
The slides, it was where the slides would appear, Brian.
Okay, so yeah, so things going into the chat or whatever are causing beeps. But I just wanted to try and get a little bit of interactivity by throwing a few questions at you. And I think the easiest way for you to respond is by using the hands up, raise your hands icon at the bottom. So if I raise my hand, it appears as an icon in the presenter view or the list of participants. So those of you who are hearing me, can you raise your hand? And just keep it raised so that I get a perspective. So great, I'm getting lots of people with raised hands, and if the people who are not able to raise their hands just probably are a little bit slow finding the button, very good. That's enough. So everyone put their hands down again. And so the next question is, do you already have access to ARCHER2? Are you able to log into the system? So that's, again, not everyone, but most people. So a more tricky question, put your hands down again, please. And this time, only raise your hand if you're having problems accessing ARCHER2. Do you need someone to help you getting access to ARCHER2? Were the instructions that were provided by David, I guess, or Claire, how you get an account with access to ARCHER2, or how you upload your SSH key to be able to get access? So no one is reporting a problem, so the people who don't have access are not interested in getting access.
There's still account creation is virtually instantaneous, so if you haven't applied for an account, you're welcome to apply now and we'll approve it. I mean, it literally takes minutes to do, so it's not a big issue. If you don't have an account, just apply for it now.
And then uploading your key is a little bit of extra work, and setting passwords when you log in. So it takes a few minutes. So, but we won't wait for you because we assume that the people who have access are able to proceed. Those of you who have access, are you familiar with building and running things on Archer? Or, well, I think we're specifically talking about Archer because I mean it's a Cray system, but every Cray system or a lot of the Cray systems have slightly different setups. So if you are, I'm seeing only 2 or 3 people who are really familiar with Archer itself. 5. So the majority have accounts, but they're not familiar with the system. So we'll take things fairly slowly. We'll try and explain all of the steps. That'll help us. Well, I'm sure it'll be too fast for some people, but if we can carry most of the people with us, then that's the best I think we can aim for. Okay, so how many of you are familiar with the tools that we're going to present? We're going to be presenting tools called Scalasca, ScoreP, Cube. Are those tools that you have used on other systems, if not necessarily on Archer? I'm seeing 6 people, so again, about a quarter of the people have used those tools or at least heard of those tools. Are there people who are familiar with other tools on other tools on Archer, such as Apprentice, or tools on other systems? About the same number, actually a few more. So a lot of you, I guess, are more familiar with other systems in Archer. They have other tools available. The nice thing about the tools that we'll be presenting, ScoreP, Scalasca, Cube, is these are open source tools. They're widely available tools. They're widely installed on a whole range of other systems throughout Europe in particular, mostly on the press sites. So if you have an account on, I don't know, the systems in Chinica, the systems in other parts of Europe, there's a good chance that the tools are already installed there. And if not, or not the latest versions are installed, we can help you get them installed there and help you use the tools there. We won't be able to do that probably today and tomorrow during this workshop, but we're definitely available, and my colleagues are available to follow up with you and help you to get our tools installed, whether it's on your local laptop or your workstation, or more appropriately on the HPC systems where you would be interested in the performance of your parallel applications. Okay, so everyone put their hands down again, and I think the most interesting question I have at the moment is, how many of you would have traveled to Edinburgh if we had had the event in person? So I'm guessing that a number of you are actually in Edinburgh, that wouldn't have been such a problem for you. But for the people who are outside of Edinburgh, outside of the Scotland area, I'm not seeing so many people. So I'm guessing a lot of people who we have on this course, because it's a virtual event, are here because it's a virtual event. Okay, let's clear the question and ask it more clearly. How many people outside of Edinburgh would have travelled to Edinburgh for the workshop if it was in person today and tomorrow? So 3 people would have travelled and would have liked to travel, and we would have liked to travel. Christian and I would have liked to travel, but we were too late getting permission, and that was why we had to make the event online. But that has the advantage that it's then open and accessible to more people than might have been able to travel. So that's we always like to do in-person events. We can see and help people better in that context. But we understand that that's not so convenient for everyone, especially while people are still working out travel restrictions and travel budgets. So virtual it is, and we hope that we did it virtual last year. We've done other virtual events. We hope that that's a reasonable compromise and works for you. Okay, so I'm going to go back into my introductory slides, hopefully, and get into the presentation. And Christian, if you're seeing any questions or things come in on the chat, then just interrupt me and let me know. The slides are going to be available. They are available on ARCHER2, and we will, David and Claire will be making them available on the website, so that where we come to the hands-on exercise, you'll have a chance to download the slides and follow those at your own pace, especially for the afternoon sessions. But this first presentation is a very high-level introduction to parallel performance engineering. It's just to enable us to make sure that the terminology that we introduce is halfway familiar to you. Performance means different things to different people, and it's changed over time, but it's not a new problem. Everyone who has been programming computers from the early days has wished that their calculations executed more quickly. They got the results faster, they got more results. And so that's why we think this is a constant challenge. The technology changes, the system changes, the metrics that people need and that can help people change, but it's a very challenging problem, and it's not getting any easier. Often it was the case that you could just wait for a few revisions of technology, a new processor, and your application would magically run faster. That hasn't been the case for a long time. You've had to parallelize your applications. You've had to be able to exploit multiple cores within the nodes and multiple nodes together. So you have a complex machine hierarchy that you have to deal with for your parallel applications. Your applications themselves are typically more challenging as well, because you're having to combine different libraries and different parts of the code, work with simulations dealing with different scales of problems, from the atomic scale up to the, I don't know, the astrophysical scales of galaxies and planets. So that's a real challenge, and for us, that's why these courses are always, I think, a valuable thing to be aware of. And even if you've analyzed your application, if you're familiar with its performance, as you move to a new system, as you change compilation options or add some new parts to the simulation, all of those introduce performance changes which you need to investigate and understand. And as you try and scale up your application to use more nodes, more processors, more cores, every doubling of scale typically introduces a new bottleneck as well. So there's always new aspects that you need to be looking into, and our tools are some of the tools that we believe are helpful in that process. There's a lot of material online on the ARCHER training archive, and in terms of using ARCHER, in terms of using the system and a lot of the Cray specific tools that are available on ARCHER, there's a lot of excellent material available. And we're not going to be replicating that in this workshop. We encourage you to refer to the available material that's in the available archives. There's also material there about optimizing codes for running on the AMD processors, which are the main processors in the ARCHER2 system, or optimizing parallel I/O. So all of those are important aspects. We would consider those sequential performance factors, things that affect the core of single nodes, single cores. And those are really important to the overall performance. Choosing the right compiler options, choosing the right application algorithms, making sure that you're dealing with file I/O adequately and appropriately. Those are all things that, as I said, are very important. And we're going to skim over them and not really deal with them in this course. You'll see some information about hardware performance, core performance and hardware performance counters that are available at the core level, but that's not really our focus here. We're really going to be focusing on the parallel performance factors, the things that affect you when you're dealing with multiple nodes and multiple cores within each node. How you partition your application problem, how you split the work, decompose it, and spread it across the cores and across the nodes. Once you've decomposed it, how the different PCs interact with each other, how you're using message passing, such as MPI, between nodes, between processes to communicate and synchronize those processes. Within a node, when you're using multi-threading, how do you synchronize the process? How do you synchronize the threads? How do you deal with locks and other aspects at the thread level? And we're going to focus on OpenMP because that's what most people use. A lot of the technology that we'll present also works for other threading models as well. So multi-threading in different ways, often combined with message passing, where you're using message passing between processes, between nodes, and then multi-threading within processes, within nodes. And that's where the tools that we present have their strengths, how you can understand communication, synchronization, load balancing, load decomposition issues are where we're going to be focusing primarily in the workshop today, tomorrow. It'd be nice if everything happened automatically, but that's unfortunately not the case. Getting things working, engineering a successful solution requires putting all the pieces together and thinking about what you're doing. You might be very familiar with your application and you might have a pretty good idea of how you think it runs, but it's always better to do some measurements rather than to guess or to just hope that things are working as you think they might be. The measurements will help you to determine where the performance issues are. They help you to compare measurements, to compare alternatives, and to validate each step as you go along. As you change things, as you modify the code, the compiler, the optimizations, every time you change things, there's a potential that things improve, but there's also the potential for things not improving as much, or perhaps not improving as well at all in the way in which you expect. So every time you change things, we encourage you to do new measurements and verify what you're changing and the impact it has on the execution and the execution performance. Modeling application execution performance is really important, really useful, but we find that it's difficult and it's challenging, and we're not going to focus on that in the course today. There are other courses that are available which can help you. If you have a good performance model, that's great. Hopefully the performance model supports what you're seeing in the measurements that we'll present and show here. And if there's a discrepancy between the model and the measurements, that's a good thing to follow up on. That either means the measurements are bad or the model is bad. And understanding which one is the problem is an important aspect going forward. What we present and consider the engineering workflow is a cyclic process involving various steps. Typically, there's some amount of preparation required. That might be negligible. It might be very simple, just adding debug symbols that allow us to see which routines are being executed and which parts of the code are being executed. And you can also engage in that process as well. You can mark the most interesting parts of your code with additional phases, additional probes that help us to distinguish what is the main part of the execution, what we might call the main focus. Typically that's a solver part that you might want to distinguish from the initialization parts and the finalization parts that might be just one-offs. So the initialization is important to get things set up at the beginning, but you might actually just measure a few solver steps and focus on those rather than run the entire solver to its convergence, which might be, I don't know, hundreds of steps running for days. You don't need to measure them all. If they're all, if it's an iterative process, you might just want to focus on running a few solver steps and focus on analyzing that performance in more detail, especially for this workshop. So we're going to be showing you small exercises that run in a minute or less than a minute on a single node. That's really, really small, just to have something that we can interact with and do a few iterations with. For your own codes, we recommend setting up a test case that will run in 5, 10, 15 minutes on one or a few nodes. And that, again, will allow us to iterate with you and do a few steps. If you have a simulation that runs for days and requires the whole of ARCHER2, we won't be able to do many measurements or any measurements during the course of the next few days for that system. And so setting up a small scale test case that you believe is adequately representative of your real simulations is an important part of the preparation, and hopefully a few of you have something ready, or you can get something ready over lunch or over the course of the rest of today, so that when we return tomorrow, you have a test case that's a more appropriate one for applying our tools to. Once you have something prepared, we're going to go through the process of doing some basic measurements where we collect some information about the application execution when it runs. Typically, we'll be initially collecting that information in memory and then storing that information to profiles or to traces at the end of execution. We then have an analysis process where we can go through that initial set of measurements and augment it by calculating other metrics or looking at things more thoroughly. And then we'll work with you to go through the interactive process of exploring those measurements and identifying what are the main problems or what we think are the key things to be looking at in those measurements, in those analysis, which can present you a lot of information, but not all of it is going to be critical or indicating bottlenecks, things that that you're going to want to modify. Then there's an optimization quadrant here where you're going to modify things. That might be just a simple modification like changing the number of threads or the number of processes that you're executing with, or changing the bindings that you're using to bind processes and threads to cores on Archer. So that might be relatively simple, and then set you up for another phase of new measurements and analysis. Or it might be that you're going to be modifying the code more substantially, putting in some markers or changing the solver that you're using, writing some new code. And all of that may be a more substantial change that, again, will initiate another cycle of this measurement and analysis process. Of course, if you modified the code, you may need to rebuild the executable and prepare a new executable for measurement. So, I mean, there are different steps in this process. Some of them you will be able to skip. Some of them might be relatively easy. Some of them might be quite involved and require more time. It's very application dependent. We'll take you through the basic cycle and then work with you to apply those steps to your own code as time is available in the afternoon sessions. Figuring out where there are problems and where it's worth spending your time is something that we consider best guided by the Pareto Rule, the 80-20 rule. In our experience, programs spend 80% of their time and 20% of the code, and you'll typically spend 20% of the effort to get 80% of the best possible speed up for your application. So with those two variants of the rule in mind, know when to stop. You can, some people get lots of fun from working on getting as close as possible to the application performance that's available on a system. But unless you're really tuning things for a benchmark or a procurement, most people are happy with 80% and spending only 20% of the effort that would be required. That allows you to spend more time on the physics and the science and the parts that's typically more interesting to the application developer. For an application analyst, for a benchmarker, they might spend a little bit more time to get closer to 100%. So that's your choice, figuring out how much time to spend and where to stop. But of course, knowing where you can get benefit and where to spend that optimization effort is what makes using the tools beneficial. If you're optimizing parts of the code that are not executed or that are only executed once during initialization, they're going to have very limited benefit and no benefit for your simulation performance. So you're not going to get so much benefit from optimizing those. So as the quote here from Knuth says, optimize what's important, and if you optimize that, then you can be happy with being productive. If you're optimizing things that don't matter, that's fine as well, but we're not going to recommend that. Just to fly through some of these slides, I'm going to mention a few different metrics. We can show things as counts. MPI messages sent and received are example counts. Typically, you're interested in how much time those spent, so the duration of those message transfers, how much time you're spending in sends and receives or different parts of the code. That's often what you're optimizing for. That's typically what you're most interested in. And maybe you're interested in parameters as well, such as how many bytes are being sent and received. And performance is an interaction of all of those. If you're sending more data, doing more messages, that will have an impact on the duration, the overall time of your message transfer. So all of that will affect your MPI performance as well. Lots of metrics are derived metrics. So we're not just looking at the basic counts or the basic time, but we're putting things together in ways where we're looking at messages sent per second or the aggregates of how much is sent per process, what is the variation across process, across thread. So often we'll be normalizing the metrics, and again, that's showing things as percentages or percentage of the maximum. Those divide metrics are often more meaningful and easier to compare than the absolute counts of how many bytes are sent, how many messages are sent, or especially when you aggregate them across all processes. Some of the metrics I mentioned are things like execution time, how many times you're calling various functions, your instruction intensity, how many cycles are executed per second, or how many floating point instructions are being executed. But there's all sorts of variations on these metrics, and you really need to know what are the details of what you're measuring and what the tools are showing. If it's floating point operations, what is a floating point operation? Is it only things like additions and subtractions, or is a load of a floating point register also a floating point operation? In principle, you can choose, and the metric can adjust to vary according to that. It may be you're interested at things at the application level, what you're doing at the application in terms of subtractions and additions, or it may be at the hardware level where it may have combined things together into vectors of operations, and you may be interested in comparing double precision 64-bit or single precision 32-bit floating point, or half precision or quarter precision. I don't know. These days, people are all sorts of have all sorts of addition. There's all sorts of optimizations you can do by reducing precision from 64-bit to 32-bit, 16-bit, or even 8-bit floating point. You'll have reduced the performance to something that is a lot less precise, but you'll be able to do a lot more 8-bit floating point instructions per second than you'll be able to do 64-bit double precision. So depending what tolerance you can, your application can tolerate, reducing precision is a great way to improve performance. But if you're losing accuracy that you need, then that's no good. You need to make sure you're getting results that you can live with and have the convergence and tolerance that that allows you to get meaningful results from the computations that you're doing. At the CPU level or at the process and thread level, you're often interested in time to solution, which is the wall clock time. The wall clock time is the easiest thing to compare when you're comparing running on different numbers of nodes. As you use 2 or 3 times the number of nodes, you would expect or hope the wall clock time reduces by a factor of 2 or 3. If you're doing strong scaling, if you're doing weak scaling where you're scaling up the workload, your wall clock times would be something you'd want to keep constant. Whereas things like the CPU time, where we're looking at the number of cores and threads that you're using, are going to increase as you use more cores and more nodes of the system. So CPU time is the aggregate across the cores and across the nodes, and that's an indication of the aggregate time. Often that's what you're going to be charged for, or you'll be charged for the number of nodes that you're using, which is again a different manifestation of this. And so if you're getting charged for your CPU time, that's the thing that you're going to be wishing to optimize. If you have an application that's non-deterministic, if your execution is doing different things every time it runs because of your choice of random numbers or some other factors that are application specific, you may need to do multiple executions to get a meaningful insight into how your application is performing and aggregate those together. Or maybe you just look at the minimum of several runs. If you're doing file I/O and have other non-deterministic aspects, because file I/O is to a shared file system where you're competing with other people doing file I/O at the same time, again, you might just look at the minimum of several runs rather than being reliant on a single execution run. Or as I said, you can do several runs, aggregate them together, and maybe that gives you a better handle on how a collection of runs or a typical run would perform. You can use the mean, you can use the median. Depending on the circumstance, one is better, more appropriate than others. We're going to be talking about inclusive and exclusive metric values. And the picture here is one way of thinking about that. The inclusive metric value, such as the execution time here for function foo, is the green part, where from the beginning of foo till the exit from foo, everything inside foo is aggregated together, including calls to subroutines, such as this case bar. So foo is calling bar. If we're measuring the time in bar separately, then we might want to consider the time that is in foo that's not the time in bar. So the part that's in orange is the time for the calculation in foo that excludes the time in the subroutines, including the time in bar, in this case here. So again, depending on what you're interested in, you may want to look at the inclusive or exclusive metric values as a guide to what you're showing and presenting and going to optimize. We'll see this more clearly in the way that the tools present this information. So different choices are available here. How you do measurements, how you process that information, how that information is recorded, and then how that information is analyzed. So those are the 3 parts that I'll skim through here. We can do measurements in 2 basic ways, sampling and instrumentation. If we're sampling, we're going to periodically interrupt the execution. So if we're thinking about a application timeline here, shown in the picture here at the top of the screen, We have a single process, a single core here that is executing, that it takes a certain amount of time, and we are periodically sampling execution here. So that's the part that is shown here by these arrows. There's 9 of them here shown, where we, every second or every fraction of a second, we periodically take a look at what's executing and take a sample at that point. And based on those samples, we have a statistical feeling for how much time in different parts of the application execution. There are different ways of doing this sampling based on timers or hardware counter overflows or different things that are going on in the execution. But they give us an approximate picture of where you are. And the nice thing is that by controlling the interrupt frequency, we can get more samples. So if we half the interrupt frequency, we'll get twice as many samples. And that can give us a better statistical representation of your application's execution. On the other hand, if we want to reduce the samples because we're running over a long period of time, if we're running over hours, we don't need to be sampling every millisecond. We can reduce the sampling overhead and just take a sample every second. But if we're running long enough, over hours and days, we'll still have a decent enough set of samples to get a good picture of the application execution. So sampling frequency is something we control to reduce the measurement overhead. What you typically can't control is the overhead of an individual sample, and a sample itself might be extremely expensive if we have to do an expensive call stack and wind and do lots of hardware counter measurements. But again, by reducing the number of things that we measure and reducing the frequency at which we sample, we can reduce the measurement overhead of the samples. The other approach is the instrumentation approach here, where we explicitly put in instrumentation at the beginning and end of different parts of the application which are being executed and being measured. So now we don't have an equal distribution of samples. We have a sample, we have a measurement taken at the beginning and end of the parts that we're interested in measuring. And that means that for things that we're really interested in, such as, for example, messages or thread synchronizations, we get much more precise information about when those are happening and what they're doing. Because when we're taking a sample inside a message event, we can see by looking at the message that we're doing, we can see how many bytes are being sent and where they're being sent to, and whether it's a collective operation, which other processes are involved, which one's the root of that operation. So those aren't available just by randomly introducing the application execution. You need to, then we have no idea what's happening inside those samples. So we would typically want to instrument the message passing events, the thread synchronization events, and get very precise information about when they're taking place and what they're doing. We may not be so pedantic about knowing about where other parts of the execution are executing. In the case here, main, well, main is executed once. We're not going to have a big overhead from that. But things like foo here might be executed very frequently. And in this case, because it's a recursive function, we may not actually be interested in seeing that foo is executed recursively 100 times and having a call stack unwind of 100 levels may be excessive as well. So saying that we're interested in instrumenting main, but we're not instrumented in foo, or we're not instrumented in foo to its ultimate level of recursion, are ways where we can control and reduce the amount of measurement overhead. Because measuring foo to its 100th level of recursion, and those small events might involve much more timer overhead and measurement overhead than actually the time for foo itself. So there's a trade-off there. You can have very high odds if you're measuring very small functions, but if we just focus our instrumentation on the parts of the application which are valuable, we can control that. So sampling and instrumentation are a trade-off. There are different ways of doing them. We'll show you some examples, and there's many more which we won't discuss. There's a trade-off in accuracy and how many events you get. And that trade-off is something that you'll be able to experiment with, and hopefully you'll see the benefits of focusing instrumentation, focusing measurement on the parts that are valuable, and just getting measurements from those. And by reducing the measurement overheads for those, you can get also more accuracy. When it comes to what we do with the different events, again, we have some trade-offs, we have some choices here. We can record everything in detail, which is the tracing approach, or we can just summarize things as we're executing and then store that information into a profile, giving us, again, an aggregate view that might be adequate for some initial analysis and help us to customize things, and when we do need to do tracing, be in a better position to trace the parts that are going to be valuable and helpful for us. So in the profiling case, we're going to be aggregating everything together. We're going to be aggregating the times, the counts of messages sent, the bytes transferred, the other hardware counters, and we can aggregate those for the different call paths of execution. We can aggregate those for each process and thread. And as we are aggregating things, we'll be calculating the totals. We can, if we want, we could also calculate the minimum and maximum. Sometimes that's adequate. But by only having the total time in a function or the total number of bytes transferred in a particular collective operation, we are losing information. We're losing the individual event information, but that summary can give us a good starting point and help us to understand perhaps how things are scaling. And by customizing and tweaking the sorts of profiles we can do, we can go into different levels of detail, and you'll see some examples of those. In the tracing case, we're going to be storing all of those individual events with a timestamp that allows us to figure out when they're taking place in the execution. That complete history of events gives us a complete chronologically ordered sequence of events about what's happening on each process and thread as the application executes. As you can imagine, the longer you execute and the more threads and processes we have, the more information we have. And as we're storing that information, or as we store that information, we'll at some point run out of memory. And as we run out of memory to store that information, we'll have to go to disk. And if we have to go to disk and flush it to disk to write those buffers of trace events, then we're going to be significantly perturbing and interfering with the application itself. So it's bad enough that we have to store things in memory, taking memory away from the application that it could use. But if we have to go to disk and write things, that's typically much worse. So there's a trade-off there in terms of how much we store things in memory versus the sizes of those message buffers. When those buffers full, writing them to the end is fine. Writing them at the end of measurement execution is fine, because then we're no longer interested in how much additional time is required. But if we have to interrupt individual processes and threads to write events, then we're going to be skewing the measurement in very significant ways, which will make analysis much more challenging and much more of an issue. This is a diagram of how things work in practice. We're looking at a couple of processes here where we have instrumented events for entering functions or when messages are sent and received. We would typically capture those events by our monitor, timestamp those, and then store those into a local event buffer on each process and thread. And then at the end of execution, we'll be writing those to separate files. Separate profiles we typically don't need, so we'll merge those together into a single profile. But the event traces, which are larger, we will typically leave those as separate files and only merge them when it comes to the analysis. If we're running things across nodes, the nodes of the compute systems these days are typically not synchronized, and so we'll typically try and do our own internode synchronization so that when we do the timestamping of events, we can do our best that we can to make sure that we avoid dealing with problems where events might seem to be received before they're sent by the corresponding node. So there are lots of technology happening in between, behind the scenes here that hopefully you won't need to see, but you need to understand here that there's buffering going on, there's merging going on, there's timestamping and timestamp correction going on, and in different circumstances those can affect the quality of the measurements that you get and the analysis that derives from those. I already mentioned various trade-offs that come into play when we are dealing with traces and profiles. Traces are great for giving you lots of very detailed information, but they require a lot of storage and a lot of disk space, and sometimes that's not very appropriate. Sometimes it's inappropriate. So avoiding the traces becoming unmanageably large, filling up the disks, is one of the things that we want you to be aware of and want to take care with, and will therefore encourage you to do an initial profile. And from the profile, we can do a thing, something we call scoring. Scoring a profile allows us to give us a good estimate of what to expect if we were to do a trace collection, how much buffer space we would need, how much disk space we would need, and also whether we are collecting events in the profile, in the trace, that are probably perturbed by measurement overheads or are parts of the application execution that are not really beneficial. So by doing scoring, we can identify those, we can do appropriate filtering to avoid them in subsequent measurements. The filtering can avoid measuring them, or if we need to, we can apply the filters at instrumentation time and reduce our instrumentation and measurement overheads substantially as a result of that. Lots of pros and cons here. We'll go through those steps and give you better insight into them. The analysis we'll be focused on is offline postmortem analysis. That event avoids us having to require resources during measurement for the analysis. So it's possible to do different forms of online analysis beyond the process level profile aggregation that I already mentioned. But having to deal with sending things between processes, between nodes, is highly intrusive. So we don't want to do that typically during measurement itself. So that's why a lot of the more sophisticated analysis is analysis that we're going to postpone and do offline after the measurements have been completed. And after the measurements are complete, we can be a little bit more, we have more time, we have more flexibility in the additional analysis we can do them more thoroughly without perturbing the measurements as we are going on. So there's a trade-off here between how much we try and do at runtime and simplify what we're collecting and measuring, and how much we postpone for postmortem, where we have time to go through things and do things in a more comprehensive fashion in more detail. So one of the analysis that we'll look at, we're not going to show you in this course, but we could in principle do a timeline visualization where we can show the events on a timeline, build up a picture where you can actually see from the events we collected in the trace, build up a picture of when a message was initiated, when it was received by a different process, and how much data was transferred in that operation. So that's very powerful. It's available in some additional tools, which unfortunately are primarily tools that need a license. So they're not open source tools, and unless you have access to a license, and I don't think there are not a license available for them on the ARCHER2 system. So that's why we're not going to focus on those in the workshop here today and tomorrow. So there's no one solution that's perfect. It's an iterative process. What's simple for what you're doing with a very small code on your laptop or your workstation is kind of analogous to what you might do working on your balcony, on your rooftop garden. As you move up to having a bigger garden and having more tools at your disposal, you might want to focus on different aspects. So having the appropriate tool for different parts of the work that you're doing is typically something that's very beneficial. And when you're dealing with HPC applications working on very large-scale systems such as ARCHER2, then you need to move to the next level of technology to have your industrial strength tools that are capable of dealing with industrial applications running with hundreds and thousands of processes running across hundreds and thousands of cores or compute nodes. And in that case, bringing in experts who can help you, experts who are familiar with the system, who can help you with the programming environment and the code that you're running, as well as experts who are familiar with the analysis tools and the various optimizations that may be indicated by those tools, mean that this becomes a very collaborative process, combining the tools experts with the application experts, with the system experts, bringing them all that expertise together to get the best out of your code and its execution on the HPC system. And just like as I was saying, you need to think about this process and what sort of measurement, what sort of analysis you're looking for will govern what sort of measurements you need to make, which will govern what sort of instrumentation needs to be done. And if you have done only a partial instrumentation, which it might be appropriate for some initial measurements, that might be missing some information that needs to be added in subsequent measurements or in subsequent instrumentation to be able to get the most complete and comprehensive analysis. So you're going to be iteratively going through this process of thinking about what sort of analysis you're looking for, choosing the appropriate measurement and instrumentation to achieve that, and then going through this iterative process maybe a couple of times at different stages of application development, perhaps in your automated processes, that as you change the code, you review measurements and analysis to see how things change, and at each stage have a good picture of what your code is doing on the HPC system as it's executing. So one slide overview of the analysis procedure. Do I have a performance problem at all? Look at the execution time. Maybe that's enough to tell you that things are going well, that you have the speed up that you're looking for, that the scalability is nice enough for your stronger weak scaling execution. But if you need more than just execution time, what is the bottleneck? Is it something at the computation level, or is it the communication level? Is it MPI? Is it OpenMP? Is it threading? Is it CUDA? Different forms of profile can help you identify what is the main bottleneck area. Where is that bottleneck? If you've done just a basic profile, then it tells you that all of your time is in MPI collective operations, or it's in MPI broadcast, or MPI all reduce. Maybe that's something that you do multiple times and in different parts of the code, and therefore having some insight into which part of the application is doing the broadcast or doing the all reduce. A call path profile will help you identify and distinguish those different parts of the execution and figure out is the bottleneck in the broadcast in the introduction, or is it in the broadcast in the solver, or in the finalization. Now that we know that we have a bottleneck and where it is, why is it there? And that's where we go to the next level of analysis, where we want to perhaps look at some hardware counter information about what's happening at the core level, or we want to look at a detailed event trace to figure out um, which of the collective operations or the communication operations are the ones which are inefficient because they have waiting times. They're unsynchronized across processes, as opposed to the ones which are maybe executed frequently but are not a performance issue because they don't have waiting time. So trace executions and trace analysis can help us get that sort of inefficiency insight that's not available or not so easily available from higher level analysis of profiles. And all of that basic digging down into where you have performance problems and why they're there is the sort of things that might help you if you look at load balance, what's happening across processes and threads, or comparing different executions, whether it's different solvers or different versions of the code, different compilers. You may need to compare multiple executions side by side at the function level or at the thread level to figure out the sorts of performance issues that are relevant for you. So that's the process. We'll take you through it quickly in the time that we have available. And as you get more familiar with it, you can elaborate on it and get things in much more detail. So that's taken an hour to finish my slides. We have time for some questions. If I get out of the slides, maybe I'll see some questions before we go into the next presentation. Were there any questions for me, Christian?
No, so there were no questions, but meanwhile the slides were uploaded to the course page. So thanks, Claire, for doing this. So you can download the slides from there and follow at your own pace.
So if someone has a question, I guess you can unmute yourself and ask it right now, or put it into the chat if you prefer. And if not, then we'll continue with Christian's presentation. So maybe Christian, you can prepare your slides.
Yes.
We'll have a break in about 30 minutes. So in 30 minutes, we'll also have a chance to have more of an interaction if Christian wants to go ahead.
Yes, so I'm now sharing my screen. Okay, there it is.
It's coming, yes. That's good.
Okay, so then welcome to the session Instrumentation and Measurement with SCORP. So here we are going to give a short introduction to SCORP and then apply SCORP to a small benchmark code and do a first measurement. So what is SCORP? So SCORP is a set of command line tools and measurement libraries that are applied in this engineering workflow. So SCORP is basically or is used here in this preparation and during the measurement. So for the preparation, we usually need to recompile your code and introduce SCORP during this recompilation step. At the end, at the link time, so we add some measurement libraries there, and the whole goal is to just insert some extra code so this hooks into your application. This is usually a one-time process, so we just rebuild your application once, and then we can run it or do the measurement here several times. So with different configurations. So configuration is usually done just by applying some environment variables. So there are different ways to collect data. So as Brian mentioned, there is this profiling way of collecting data and also the tracing way. Both is supported by SCORP. So SCORP also provides some provides a command line to do kind of analysis. So it's was already mentioned by Brian. It's the scoring part. So SCORP score can be used on a profile measurement to estimate the size of a trace measurement. So this is usually quite helpful to prevent traces that are too large to fit into a memory buffer. Okay, well, okay. So yeah, as already mentioned, so SCORP is this infrastructure for instrumentation and performance measurement. So and SCORP can be used to provide several results. So the default ones or the built-in ones are this call path profiling. So we create a profile in a special format. It's a Cube4 format that then can be analyzed by the Cube GUI, which will be presented in the next session. But we can also do some event-based tracing in a special format. It's called OTF2, which can be used by several tools. So, for example, the Scalasca tool, which will be presented tomorrow. So we usually try to support every parallel paradigm that is relevant for HPC. So, of course, we support MPI and SHMEM, OpenMP, and pthreads, and on the accelerator side, so there is CUDA, OpenCL, OpenACC, Cocos. We are working on HIP and also on OpenMP device events. So SCORP is it's an open source project, so you can just download and modify the code or contribute back if you want. So we got funding, or the initial funding, from the German government, but also from the Department of Energy in the US. And we from there on we got several third-party project funded the development on SCORP. So here an overview on how it looks like when your application is instrumented. So the light green box here, this is your application, and the dark green boxes here are the hooks that during recompilation got inserted into your application. Here on the right side, we also have this blue box. So sampling works a little bit different. It's not supported on the ARCHER2 installation here. And so I consider this still a little bit experimental, especially when it's used together with OpenMP threading. So on other systems, it is available. So it depends on a special library that was not yet available on this ARCHER2 system. So, but we will concentrate on the dark green boxes here. So as mentioned before, so we have this process level parallelism, MPI and SHMEM. We have different ways to intercept this thread creation and thread destruction and joining of threads. There's something for accelerators. There's also some I/O, so some special I/O interception. Also memory allocation and deallocation, which is not mentioned here. And of course, we can do the source code instrumentation, as Brian showed you in one of the slides. So where we get or we insert some code at the beginning and at the end of each function. So there are different means to get the hooks into your application. So basically, there are 3 ones. So you can do it at compile time, you can do it at link time, and you can use some tools interface that is provided by for example, CUDA. Yeah. So compile time is used for the source code instrumentation. So several compilers provide switches to insert some callbacks at function enter and function exit. For OpenMP, we do some source-to-source processing. So then, when with compiling, the hooks get inserted there. There's also the way of, or you can also add some SCORP provided pragmas, or not pragmas, sorry, some defines in your code to define the regions that you're interested in. So this might be useful if you have some coarse-grained stuff. For example, you have an initialization phase, kernel 1, kernel 2, finalization. You can add some user instrumentation there to get really some coarse-grained stuff that or something that is splits your application into some basic blocks. So then there is this link time way of getting hooks into your application. So for example, for MPI, we provide our own MPI wrapper around the real MPI function calls. So so then if you call MPI send, for example, this MPI send call triggers the SCORP measurement library. We query some additional information or just get it from the arguments, for example, how many bytes are being sent, and then pass this to the SCORP measurement core. So the same or basic same principle is done for tools interfaces, so that are provided, for example, also by OpenMP, but this is still work in progress, and so also by CUDA. So for example, CUDA provides this kubd library that we use, and if we get events from this library then, or from this interface, we augment it with some data and pass this to the measurement core. So basically this here is the measurement core. Every event gets or has to move through this measurement core. There we get a timestamp for each event. We store it in a thread local buffer, and optionally we augment it with some hardware counters. So for example, we have this PAPI hardware counter library that is used within SCORP, or R usage counters, perf counters. And you could also use or write your own plugins if you, for example, have some special energy measurement hardware, and this can then be feeded into the SCORP measurement. Then once we have everything ready for the event, we can pass it either to a call path profile event consumer, or event traces event consumer. So here we just show the two standard of them, so the call path profile and event traces. But here again, you can also write your own event consumer using a plugin. But this will not be covered here in this course. So usually we start with the call path profiles, and this will create then a single file as output. So kube profile that can be then analyzed with different tools. So in this course here, we will see how it will look like in this Cube GUI tool, but you can also use the tool Paraprof, which comes with the Tau package from the University of Oregon. You can also feed several of these call path profiles into a tool called Extra P. It's a modeling tool developed at Technical University in Darmstadt in Germany. You can also use or feed several of the cube profiles in a tau database and then do some correlation analysis there. Yeah, and I mentioned earlier, there's also a SCORP command line tool called SCORP score. This can also be used, or this is used to estimate the size of a trace buffer. So this we are now moving here to these event traces. And before doing an event trace, it's usually good to estimate the size and to then adjust some measurement environment variables so that the entire event trace fits into a process local memory buffer. So the event traces then can be consumed either by a timeline viewer, for example, the Vampire tool from Technical University in Dresden, or can be feed into Scalasca to automatically find some wait states and the root causes of wait states. We will learn how to do this tomorrow. And Scalasca then itself creates a call path profile again that can be then be analyzed by all of the tools I just mentioned here. So we started developing SCORP in 2009. So as I mentioned, we got some initial funding from the German government and from the Department of Energy in the US. And these are the initial project partners. So some of these, we didn't start from scratch with SCORP because there were tools before. But there was a tool called Vampire Trace, for example, for mirroring stuff, which came together with the Vampire tool from Technical University in Dresden. Then there was the EPIC measurement part that came with Scalasca, and their tau had their own special measurement infrastructure. Everything worked quite well, but so you couldn't use just a single tool for instrumentation and then use several tools for analysis. So every tool had its own format, and we ended up writing some output file converters, which was quite tedious, and this approach didn't scale, and therefore we joined our forces so to provide a single measurement infrastructure, that then can be used with several analysis tools. And I saw there was a question. Can you explain again the difference between event traces and call path profiles, please? Yeah, okay. So so call path profiles, it's basically an aggregation of information. So you just collect how often a function foo was called and from where, but you lose information about the individual calls. So this is then with event tracing, it's different. There you record every single call to this function with a with an individual timestamp. So here the thing is that the event traces or the size of the event traces, they just grow linearly with the number of events. So where the call path profiles basically have a constant size depending on the regions or on the functions you have in your program. So, and this is the reason, so you have nearly constant size call path profiles. Therefore, we do the call path profiles in the beginning and then do some estimation with this tool called SCORP score to see how much space the same measurement would require when doing event tracing. Okay. So yeah, and now I think we can already start with some hands-on. Okay, so after this quick introduction to SCORP, we now will do 2 measurements. I think I can move one page further here. So we have a small benchmark application that we use throughout this tutorial here. So first we will do some reference run just to check if everything works as expected, if the output is what we expect, and we can also take the measurement time that an uninstrumented application would use. The next step would be to instrument the application using SCORP. So this would mean recompilation and somehow introducing SCORP into the build system of the application. So this is usually straightforward, but sometimes there are some unexpected and tricky obstacles to deal with, and so there are several ways, and we will talk about this. Once the application is instrumented, we can do measurement with basically the default settings, and then once we have this, we will look at the result using the cube tool. So so is this font size here is this large enough? Can you read this, or shall I increase the? If I should increase it, please raise your hand. So where can I? Okay. Sorry. Oops. Okay. So we need to log into the ARCHER2 system. So usually this is done, or we should do this with the -X. So because we want to launch a GUI tool afterwards. So usually this is done by providing your username and then login.archer2.ac.uk. So just replace your username here instead of felt2. So and for me, I do it a little bit different because I don't have a standard named public key. So for me, it's ARCHER2 and the name of our course. So then in addition to the SSH key, you need to provide a password. So let's see. This is password. Okay, and the screen should look something like this. So I give you a little bit time to log in. So is it the password to the safe account? Okay. Let's see. So for me, it's not the safe account or the safe by EPCC password is something different for me, but okay, and you're having problems with the dash capital X. So then I think
okay, so
yeah.
Mark, which how are you logging on? Are you using MobaX term or I don't know if maybe you can hear me, but I wanted, are you using, is it a Mac or Windows machine or Linux? That's a bit weird. And Syed and Elisabetta, I hope I pronounced your names right. Syed and Arena, sorry. I wonder what platforms you're using. We can do it. Okay. Oh, so maybe I'll do a screen share. I'll do a quick screen share with Mark. Is it okay if I do a quick screen share with you?
For this first exercise, we don't actually need the X GUI. So as long as you can log in and run things, that's sufficient.
Okay. I'll maybe try and sort it. Oh, yes. I think that yeah. So yeah, it does create the X authority the first time you log in, and maybe there's a delay or something. So maybe Irina and Syed, if you could log out and back in again. That's the usual. So, sorry, Irina, I don't understand. Okay. Yeah. I don't understand that X is a mystery, but I think it sets up the X authority file the first time you log in. I've seen those kind of messages coming up. So I've, X authority created or something like that. So maybe you have to reconnect. I'm not sure, but I'm happy to do a screen share. I mean, I don't want to hog the session. Sorry. Okay, fine. I think that's the issue. I think there's just a slight, yeah, I think it sets stuff up the first time you log in, and for some reason, yeah. Fine. Okay. Log out and back in again. Okay, that's fine. Great. Thanks, everyone.
So then I will continue. So for this session here, and also the sessions tomorrow. So we are going to use the GNU compilers here on this system, on this Cray system. So usually on Cray systems, you select compilers by loading a progenv module. So the standard module that is loaded by default is usually the progenv Cray here. And we need to switch to the progenv GNU for our session. So the reason is that although we usually try hard to support every HPC system, sometimes with new machines there are some surprises. So for example, we run into an issue on with progenv Cray when we combine Fortran and C code, and then at link time we get some strange unresolved symbol messages that were already reported to Cray, but haven't been fixed on this new Cray EX platform. So therefore, we installed a SCORP-P or Scalasca module also for Program Cray, but there we had to deactivate the Fortran support. So, and as our small benchmark that we're going to use is in Fortran, so here therefore we have to use Program GNU. But if you have a C or C++ code, you can also, and you prefer the Cray compiler, then you can also use a different module than for doing the instrumentation this afternoon. So we are going to do the tutorial in the work file system. So this is the reason is that as far as I know, there the compute nodes cannot access the home file system. So therefore, we build everything on work file system. And so to do so, we can cd into this directory here. So TA, I think it's for training, and so the number is the training event here, and then there is a single directory per registered user. So if there are any problems in following these instructions here, then just raise your hand, and then we will deal with it. So we prepared this little benchmark. So there's a tarball that we need to extract here. So let's see, in my directory, so nothing is there. So we can then extract this tarball. This is also in the work file system. And it's in a different directory. It's y23 / shared / tutorial, and it's called npb 3.3 and so on. And we just, or everyone, please just extract it into your directory. So here it is. We cd into this directory, and then from there work on this code. So then just like to mention, so for this afternoon, if we need to exchange some data, then we can do this using this directory here, but we will mention this again. Okay. So so we are using this NPB MZ MPI suite benchmark. So it's a NAS barrel benchmark from NASA. It's a quite dated benchmark. So there it's highly optimized. So we won't find anything that we can improve here. But this is an improvement, or it's not the optimization is not the target of the of this course here. So we use this because it's very portable. So it runs on nearly every system that provides a Fortran compiler. It's easy to adjust. So the build system, it's just a set of make files and a config file. So it's easy for us to introduce SCORP-P into this build system. So this is basically the reason why we use this code. So it's nothing special about it. So it's just a convenient code that is known to provide no special surprises on if you move to a new machine. So this benchmark comes in three. Well, there's in three variants. So we are using this BT-MZ variant here. There's also this LU-MZ and the SP-MZ, but so we concentrate on this BT MZ here. You see there's comes with a make file and a README and a tutorial. So, but for now, we just try to build it, just type make and see what happens. So here we get some information about this benchmark here. It says, or it mentioned this benchmark name. So there are these three versions I mentioned. Then there's this class, which is basically the problem size. So S is, I think, is small, then is workstation, and then it increases from A through F. And we also need to specify the number of processes. So because this will be hard coded into the code. So for this machine here, we recommend to use the BT-MZ. This is clear, and we want to use the class C using 8 ranks. So this is for this first usage of the tools. It's a suitable configuration. So at the moment, so no score P is involved. We are still at this making or producing this reference run, so to see if everything works with our environment. So we can now build. Well, that's not true. First, I want to show you how to configure the benchmarks, how to set some compiler specific variables. So we can go into this single config file of this benchmark here. So it's called make.dev, and it's in the config subdirectory. We will adjust this. This is for this code basically the build system and the file that we need to modify once we are going to introduce score P into the build system. So just have a look here. So there are some compilation flags and linker flags and some specifications for the compiler. So so here, for example, we have the commented outlines here is for the Cray compiler, then for the AUCC, and here the one is for GNU. So here you see that that we use an fopenmp flag. So the I did mention this. So the code is a mix of MPI and OpenMP. So we activate OpenMP using this flag here, and as the GNU compiler became a little bit more or is now more standard conforming, we and usually or quite a few MPI programs are not, so we need to provide this fallow argument mismatch flag. Beforehand this was a warning, it's now an error, and with this flag we switch back the warning, the error into a warning. Okay, we are using here this MPI F77 compiler, so we use this FTN compiler, which is the name of the Fortran compiler on Cray systems, and that's basically it. What is interesting here for this reference run. Then we build the program. So make BT that and using class C and 8 processors or 8 ranks. And so just do this. So you see here that we are compiling several Fortran files. using the flags that were shown in this config make.dev file. And at the end, we are linking the file. I think it's yeah, linking is here, this line, and we built this tool in a bin subdirectory that we can cd into and do an ls. And here we have this program that we just built. So could you please show the last command again? So you mean this one? So it's also, I think, here on this slide here. Yeah. So this is the command here used for building the code. It's for building the reference code and also later for building the SCORP instrumented version. So, and once this the build step is completed, you can find the the uninstrumented program in the bin subdirectory. So nprox is the number of MPI ranks. So the MPI threads, the OpenMP threads are specified separately using the OpenMP num threads variable in the job script. So nprox is just the number of ranks here. So to run this program, we need a job script, and we prepared one. So this is in the job script directory under ARCHER2, and there are 3 files. So this run sbatch is the reference run, and then there are 2 others that will be used later during this course. So we just copy the run.sbatch into our bin directory. So we can look into this script. And I'm not sure. So here's something about the reservation. Usually the when I did the testing last week, the jobs went through pretty smoothly. So, but if you want to use the reservation we have for this course, then use just these 2 lines here. So this sbatch -qos equals reservation, and then the reservation specification here. There are 2 ones, one for Monday and one for Tuesday. So this should work. I haven't tested this with the reservation, but so yeah, should work. Then here again, we need to set up the job environment. So basically switching from the proc and cray module to the proc and GNU module. And then here we have some configuration for the benchmark. So just we just done using environment variables. So there's the NPB variables are variables recognized by the benchmark. And then we have we specify how many OpenMP threads are going to be used. So here we are just using 6 threads. And we do some placement of the OpenMP threads. So, but this is just for this for this benchmark code, you usually know how to do this or for your own codes in an appropriate way. And then here in the end, we launch the application. So CPU per task is 16, but open OMP num threads is 6. Yes, so we are not going to use all the available threads, but I'm not 100% sure why we set it to 16. Brian, do you know? So the CPUs per task.
I think 16 is the maximum that could be used, and so we just left that, and then you can modify the subset that you're using through OMP threads. But
yeah, okay.
It's not necessarily optimal, and so the experts can feel free to optimize this configuration and improve it. As long as it runs for everyone, it's good enough.
So, okay, I just changed the reservation here, and we can now submit. And we use the SBatch program on the system to submit this this job script. So let's do this. We can look at the queue using the sq-u-user $user command here and see what's going on here. So it's already running. So it usually should run in, I think, 12 seconds or so. So yeah, it's already done. So, and we see here that we have one extra file here. So this output file, and we are going to look into this file. And so it starts with something from the system. And here we see the start of the output of the NASPERL benchmark. So first some information about how many processes, how many threads, and then you see that the benchmark is doing 200 time steps simulation. I think it solves some Navier-Stokes equation and provides then some results. And what is also good to check if the verification is successful. So this program here provides this information, and once we use score P, we also should check if the results are still as expected. So this benchmark here gives us also the runtime. So it calculates the runtime by itself, so some internal measurement, and then provides this as an output. So this will help us once we introduce score P to see how much overhead the tool or the score P tool would introduce. So which I think is an indicator of how good the measurement will be. So yeah, that's basically it for the reference run. So what we did so far is we logged into the system, we switched to the work file system, we unpacked a small benchmark code, we compiled the benchmark code without any tools, and then we executed this benchmark, or we built it with 8 MPI ranks, and we executed it then on 8 MPI ranks with 6 OpenMP threads each, and it ran to completion. in roughly 12 seconds. So that's good. So we are set now to introduce the Score P tool.
Christian,
so,
do we want to take a break here?
Sorry?
Do we want to take a break?
Yeah, maybe we can have a 5-minute break or so. Or is it already 15 minutes you propose?
David, what do you suggest?
What time is it? I would have thought maybe I don't know what you're saying. It's maybe a 10 or 15-minute break just to let people get a coffee or.
And we can follow up with people who still have problems and questions. But I would suggest well, 10 minutes would take us to past. But I think we should give people 15 minutes, so maybe 25 too.
Yeah.
So Gavin, in the script, I changed the reservation here. So I commented these 2 lines here and uncommented these here. This was the only change I made. But so last week I was able to use this reservation settings here. Okay, I fixed it. Okay. And now you are able to submit. Yes? Okay, great. So then we continue at past or
11:35.
I said 11:35. I thought that's okay. Just give people a little break.
So yeah, then I'll be right back. So I think it's time to start again. So before the break, we just did this reference run of this VT benchmark. We just used the default build system and used the provided job script to see if the program is able to build and able to run. This seemed to be the case. So in the configuration of 8 MPI ranks and 6 OpenMP threads per rank, it ran in under 12 seconds. So now next step would be to introduce Score P. So basically to insert the hooks into the program. So we do this by recompiling the program and introducing Score P into into the build system of the application. So therefore we just cd back to the top level directory here of the application. So this is where we started. So now we need to modify build system of the application. Here it's quite convenient. So the build system that is relevant here is just this single file. So we just modify the file and then rebuild the application, and then we are done. So where do we modify the file here? So Score P is usually used as prefix to the compiler. So here we had the old compiler command, so it's just using the ftn Cray compiler. We won't use this for the next session, but we will use here this MPI F77 equals score P, then a score P option, and then the usual FTN compiler. So this is depending on your build system, the only modifications you need to do. So you usually just prefix the compiler with a score P command and potentially some score P options. So if your application uses a CMake or AutoTools based build system, then this approach will not work. So therefore we have some special compiler wrappers that will be introduced a little bit later, but before we start in the afternoon session, where you can use score P on your own code. But for very simple build systems, prefixing the compiler will just work. So this is what we have done here. So we just use a different compile command, and that's it for introducing score P and for inserting hooks into the application. And by providing different options to score P, you can select which hooks will be inserted. But here we will go with the default, and in addition, activate user provided macros that were already put into the the application. So we just save the file, and that's it for introducing score P. So we need to clean the environment here. So because the object files are still lying around, so we delete those, and then we can use the old compile command again. Oh, here it is. So David wrote a lengthy chat message. Yeah, okay. So yeah, so I mentioned that the newer GNU compilers are more picky about Fortran, and that quite a few MPI, older MPI Fortran codes are now considered being invalid, and you can switch them back to invalid by providing this GNU compiler option. So yeah, but now we want to rebuild the application here using score P. Yes, but score P does not support MPI F08, so we are working on this. Yeah, okay. Let's rebuild the application with score P. Okay. So score P not found. This is true because we haven't loaded this module. The score P module is provided here on the system, but first we need to load EPCC module other software, and load. Apps. So I can't see this because okay, that's other software. So yeah, it's EPCC. Oh, 2 typos. So wait, so and now Scalasca module is available. So I think there are more than one available. Let's see what is available. So there is the GCC one, which is a default. And so it not only loads Scalasca, but also Scorpy and some other libraries that are used with Scorpy. So OTF and so the source-to-source OpenIP instrumenter and some Cube libraries. So we are going to load Scalasca. So and now we have a Scorpy command line tool here. So with all the command line tools that are provided with this module, you can usually do a Scorpy or tool -- help, and you see the options that the tool provided. So here we just use the -- user, which is it's here. So it says it enables user instrumentation. So usually during instrumentation, you don't need this, don't need to specify these options here. Scorpy tries to be smart enough to parse your command line to see if there's MPI in the program or OpenMP. So if there's an FOpenMP option on the command line, then Scorpy itself switches on OpenMP instrumentation. So compiler instrumentation, so this inserting hooks at the beginning and the end of each function, is on by default. But not everything is is on by default. But for this small example here, with the -- user, we have everything we need. Okay, so then let's try again with making with building the benchmark with Scorpy support. So or maybe I just show you again that if you just type make, the build command is here at the bottom. So this is the one we want to use. And now you see here that it builds the same Fortran files as before, but we have this Scorpy -- user in front of this compiler. And this is also true for the link step here. So here's the link step. And it will build a binary in a bin.scorpy subdirectory. So yeah, what is done here during compile and link step is that we introduce some hooks with we use different ways. So at compile time, for example, the OpenMP hooks and the function enter and exit hooks are inserted. And at link time, the MPI hooks are inserted. So we can go into this directory. Let's see, here is the benchmark, and we can also see that it links against some Scorpy measurement libraries here. So everything starting with libscorpy belongs to the Scorpy tool, and there are quite a few libraries that are necessary to do the measurement. Okay, here again we need a job script. So and it's similar to the one we used so far. but there are now new options to configure the measurement. So we can just copy the job script from the job script folder, then in the ARCHER2, and now we copy the scorp.sbatch file to our local directory. So here it is. So we want to look into it and modify it if necessary. So here the upper part is basically the same as before. So we again make these changes to the reservation. So we comment these two lines here. The old ones, they still should work, but so we want to use the reservation here. We set up the job environment as before. We have the benchmark execution and configuration as before. And now in addition, we have this measurement configuration here. So there are several scorp environment variables, and the only one that we are going to use now is so the scorp experiment directory, which specifies the name of the directory where we will collect then the measurement data. So if we don't set this variable, scorp will still work, but then the output directory is named scorp dash and then a very long timestamp. And if you do several measurements, it gets a little bit inconvenient because you don't know what you have measured. So, and as we are going to do profile measurement or summary measurement, it's also called, we call the directory scorp bt mz and sum for summary. And that's basically it for the very first measurement. So launching the application hasn't changed at all. So the only thing we had to do, we had to recompile and relink the application. So scorp, well, so we just rebuilt the application using scorp, and we have now this binary, and we can run this binary in lots of configurations without further recompilation. And we do this by specifying environment variables. So, and to get a list of the environment variables that specify that define a measurement, you can use a tool called scorp info. So this can do several things. So it can show you a config summary. So this is basically information about the specific scorp installation. But here we are now interested in the config variables. So and here you can add another flag -full, and here you see now the configuration variables that this particular installation of scorp provides. So for example, if there's no CUDA available here on this machine, we don't see any CUDA environment variables, but on a different machine, so you would see more or different environment variables. So you also see the default here. So we start with the profiling measurement, which is by default true. Tracing is false by default. And all the other ones are not really needed right now. So except the scorp experiment directory that we set in the job script. So, but if you want to have some specific metrics switch on and off, this is a way to do this via the environment variables that can and the list you get using the Scorpy info config vars command. So yeah, now what is left is we need to submit this job. As before, nothing special here, and wait until it's finished. So it's already running. That is good. So there was a question. So there's no source code change if you just reconfigure the measurement. You can do changes in your source code by inserting some user macros, for example, to do some coarse-grained or to add some coarse-grained regions of interest. So, for example, you can put a begin and end around a kernel or around the initialization phase. And we will come to how to add this user instrumentation at a later stage. So there are some slides about this. But for the usual measurement, there is no change in the, or no active change, I would say, in the source code. For OpenMP, the Scorpy instrumenter does some source-to-source instrumentation, but this is behind the scenes, so you won't see it, and your source code isn't touched. It's copied somewhere else, and then these OpenMP functions are inserted in a copy, in a preprocessed copy of the code. So, but don't be scared. So we won't touch your code in your source directory. So let's see. So it's done, and we now have Slurm output as expected, and in addition we have this this directory here. So let's first look into the Slurm output. If there are any warnings or errors. So the top here is as before, then here the NAS barrel benchmark output starts. Again, we have this 200 time steps. Verification is still successful, that's good. And here we now have this time in seconds that increased significantly, so from around 12 to 41. This is something we are going to address later on today. But otherwise, the measurement, so the very first measurement with just some defaults, just succeeded. So, we can now look into the experiment directory that was created. So, and we see 3 files here. So the manifest file, the profile.cubex. So this is the measurement output, and we also see a Scorpy configuration. So let's look at the manifest and the configuration file. So the other files, so the real measurement, we will use the cube tool to look at this. So the manifest is basically what to expect here in the directory. So sometimes you can look at this in the case of errors, if stuff was still created as expected, or if something missing. And it also tells you that or which of these Scorpy environment variables were set explicitly. So here we just set the Scorpy experiment directory explicitly. This might help if you want to rerun the measurement. So then the other file is, oops, the scorp.cfg. So this contains the list of all environment variables and their values that were used for this one. So it's also helpful if you want to rerun this specific measurement in the future. So for the profile.cubex, we will use the cube tool to look at it, but first I will go quickly through the slides if there's something I need to mention. So this here I already mentioned. So if you have a CMake Auto tools-based build system, don't use this prefixing approach, but replace the compiler. We will come to this later on. So the configuration, we mentioned this. Yeah, okay. So then now we are looking at the first measurement using the cube tool. So there are two ways. You can either use some provided container on ARCHER2, or if you have cube installed on your local system, you need to copy over the measurement. If you weren't successful in doing the measurement, so there are reference results available here in this work TA66 shared examples directories that you can use as well. So then I think Brian, you can take over using Cube, and I stop sharing my screen.
Are there any questions for Christian yet? Before we switch, or while I'm switching? So, Christian, are you seeing my slides?
Yeah, I see your slides.
Hi.
Okay. Was that a question?
Yeah, I was just wanted to ask you a question. I was hoping more or less like when we use on-site system, when we somewhere where you want to see, for example, some loops, how long it takes, we put it in, or we want to see how the data movements are, something like this. I was hoping that something we should see also in Scorp, how it. I'm sorry, I fail to understand how these measurements are working with my source code, for example. Am I clear? I'm not sure.
I'm not entirely sure. So you use Insight systems to also generate trace measurements, and
So
then
for example, yeah. So for example, I want to understand the exercises we did, how it is communicate with my source code. Like, do we change something in the code? Like we put somewhere where we want to have measurement, or is just how we compile with the hooks with the Scarpy?
this was automatically measuring everything. So it was measuring all of the MPI that was done, all of the OpenMP that was used, and it will also give you information about the different functions that are executed. So there was no need to do any explicit instrumentation manually. We actually do have some explicit instrumentation in there, and we were enabling it with the -- user switch when instrumenting, but that's an option. It wasn't critical.
Okay. No, thank you very much. Now it's clear.
And I think that also with Insight systems, you also don't need to instrument anything. It will automatically give you information about MPI and CUDA usage, but Insight systems doesn't give you information about your source code unless you do the explicit annotations. Those explicit annotations are not done and not necessary here.
Yeah, but in Insight system we tag some part, right? So for example, where we implemented, let's say if I take OpenACC part and I want to just tag that section, Insight system can give some information, no?
Exactly. I mean,
Actually
Insight systems can be used to isolate a specific part of interest or to provide additional information. And Scorpy can do that as well, but you don't need to do it by default. And we'll therefore show you those examples later.
This is actually very nice. Thank
you. It's all a matter of what are the defaults, and whether you get too much or too little by default is a matter of circumstance and personal choice. So we're kind of sticking as much as possible to the defaults, but you can certainly customize measurements to get more or to get less, depending on what's appropriate for your specific test case. So far, we haven't actually seen very much about the measurements, and so that's what we'll see with Cube, which is our GUI. That's the equivalent of the Insight Systems GUI. I mean, it's, yeah, comparable to the Insight Systems GUI, but it's just looking at the profile information. So let me try and figure out where I am at the moment. I stopped sharing, I think, so I have to go back. No, it says I'm still sharing.
You're still sharing.
But it's not full screen. So let me stop and try again. Okay, I have the Cube analysis report exploration slides.
Yeah.
So this picture on the right-hand side is what I was saying is it's a static image of what you will see with the Cube GUI. So Cube is a package of different pieces. It includes a bunch of libraries for reading and writing reports, which Christian already said are in Cube format, CubeX format. And there's utilities provided for processing those reports. We'll perhaps show you some examples of those, although there's other ones which are used automatically. And then there's the GUI, which is the explorer for working your way through these analysis reports and seeing what they contain, and also figuring out where bottlenecks and performance issues are. Cube is part of the Scalasca toolset, and we'll see more about Scalasca tomorrow, but it's a separate component which you can install separately. And since it's a GUI, you might find it more convenient to install on your laptop or desktop or workstation, as opposed to running it remotely on Archer. But we're just going to show you the use of it on Archer, because that's most convenient for us at the moment. As Christian said, if you're using it on Archer, you're going to be using SSH-X to connect to Archer and then load the Scalasca module, and then you'll be able to run Cube with one of the profiles. Or you could install Cube locally on your workstation, on your desktop system, and then either use something like SSHFS to mount the Archer file system on your local machine, or you can copy the file with SCP or something and then run everything locally. Those are your basic options. What we're going to start with is looking at some measurement that are provided. You'll find these on ARCHER2 in this directory here, work Y23 shared tutorial samples. That's going to be the example that I look at, and we'll come back to that in a moment. But first, a little bit about Cube itself. So Cube, as the name might imply, is designed around this notion that we have three-dimensional data. We have data that is coming from three orthogonal axes that are captured in a measurement. We have a set of performance properties or performance metrics, and that's going to be one axis. We have the different call paths of execution, and we call that the second axis. And then the third axis is the different processes and threads, different compute nodes, different GPUs that where your application processes and threads are running. And by selecting one or other of those axes, we can drill down and see a lot of detail about what's happening for a specific metric on a specific process or thread for a specific call path. This is presented in the 3 coupled browsers, and those browsers allow us to interact with the data and expand and collapse things in different ways. The basic presentation is to present things as values. Values are what we like to see for precise comparison, to know exactly what we're looking at. But if we're looking at hundreds and thousands of values, it can be a little bit overwhelming. So we also use color coding, and the color coding helps us to easily identify hotspots, extreme values, which are high, low, or at different parts of the spectrum. And by expanding and collapsing the nodes, we can see inclusive and exclusive values. And that's easiest to see and explain when we actually see that happening in process, in practice. And then there's all sorts of other customizations, which we'll show you a few of, and there's lots more for you to explore on your own. So as I said, there's 3 dimensions, and those are 3 coupled browsers, which are in 3 panels. On the left-hand side, we have the panel with the performance metrics, such as the execution time, the number of visits to something, so how often it's executed, and things like how many bytes are sent and received. In the middle, we have the program, and the program is structured as a call tree. And as we expand that call tree, we see different levels of detail. So here it's already expanded a little bit. We started off looking at main. As we expand main, we see that there's some initialization, some setup, and then there's some additional parts which are more interesting, which is actually the solver part of the code, which is where most of the time is spent. I can tell most of the time is spent here because of the color coding that's according to the bar at the bottom of the screen here. So this yellow color is somewhere in the middle, 20–30% of the execution time. And then on the right-hand side, we have the different processes and threads of execution here. This case is 4 processes, each with 4 threads of execution each. This is just a basic example. I want to go back and look at one of the measurements that we actually have done on Archer itself, and we'll find that in either the directory where you've got a measurement, and if you didn't get a measurement, if you don't have a cube file, you can go to this directory and then look at one which we prepared earlier. Okay, so now I need to switch. I will stop sharing that, and hopefully I can get to my window, which is here. So I'm on Archer here in this window, which I'm hoping you have a chance of seeing at the moment. And inside this directory, there's a number of measurements which we can look at different points, but the one which is relevant to start with is this one here. And I've already got the modules loaded, so I've loaded Scalasca. That means that I have cube on my path. If cube is not on your path, you don't have the module loaded. But if I start cube here, then it will bring up the GUI for me and allow me to load the measurement. I'm guessing that you're not seeing cube because it just started for me in a separate window. So I'm going to close it, and it's specified on the command line. If you've just done a measurement, you'll have a directory containing the profile.cubex, and so that's the file that we could load into cube from the command line, as I'm hoping you're seeing here. that's going to bring up the GUI in a separate window, and so I'm going to have to switch to show you that window. Try that again. Let's try this one. That looks a bit better, and I'll make it full screen, or hopefully making it full screen is a little bit better. Christian, can you confirm that Cube is being shown full screen?
It's shown full screen, but the font size is quite small.
Yeah, so that's why I'm going to hopefully make the font size a little bit larger. That's a horrible mess, so let me comment about that. Okay, that hopefully is large enough to see now, or larger still.
For me, it's okay.
I think that should be large enough. I don't hear anyone screaming, so I'm going to go ahead with that. So as I said, on the left-hand side, we have the metrics, and the one that's shown by default is the number of times that something has been executed, and that's probably not very easy to understand. So let me select the time metric from the panel on the left-hand side. As I change the selection here, the values to the right are changing. So I've now got time selected, and this is the aggregate CPU time. If I expand the right-hand tree, I see my 8 processes that were running, and in each of those 8 processes, I see the 6 OpenMP threads. Everything was running on a single compute node, 8 processes, each with 6 threads. And as I expand the tree, I see that each of those threads was taking roughly 40 seconds of execution time. There's too many threads here for me to see them all, but in principle, I could expand all of them, and then I can scroll through and see the individual values. So this 40 seconds here that is being shown corresponds to the 40 seconds of execution of each of the threads, and then in aggregate for the 48 threads, I then have this number here, which is about 19,000. Sorry, 1,900. So all of the values from the right-hand side have been aggregated, going from the panels to the middle and then to the left. And if I, for example, expand the middle panel, I can see the different parts of the execution that are in there. At the beginning was the MPI init. MPI init is very important, but it's not very interesting. MPI init is executed by the master thread of each of the processes. And it's one of the first things that's executed before any other MPI is used, before any other work is done. If I switch to the visits metric, I see that each process executed MPI thread exactly once, which is more or less what we would expect. And then the aggregation of the one execution per process gives us a value of 8 in the middle. And then that 8 combined with all of this other stuff in the middle gives us this large number here, which is not very meaningful. What the color coding, let me go back to the time, because the time is, I think, the more intuitive, the more relevant metric. I see that the execution time for the MPI thread is about 0.12 seconds.
So, Brian, I didn't want to butt in, but it's something quite interesting there that using Scalasca, I found that MPI init, well, you've got MPI init thread there, can take out, how many nodes for this run on? It's just this one, it's just one node.
This is a single node.
You can see it's quite a lot of time. A second's quite a long time, and that grows a lot on multiple nodes. So that explained an issue that I couldn't understand why my MPI program's internal timings were always a lot less than the external timing. And that's because MPI init takes a surprising amount of time. And that was interesting. Scalasca picked that up straight away.
Well, you have to be cautious here because MPI init thread is the point where Scalasca initializes a lot of its measurement. And one of the things which it does as part of init thread is to create the directory which it's going to write into. So it's going to the file system and it's creating that directory, and it's copying the ScoreP CFG file, the config file. That's going into that directory all during MPI init thread.
Okay, but I think that's an additional fact. That's interesting, actually. I still think there is a lot. That's interesting, though. That is very interesting. Would that grow dramatically with the number of nodes, though, or not?
Yes. So it will grow as the number of nodes, because each node will be checking that they can access that directory so that they can write into it when necessary. And the other thing is that when you're running multi-node, ScoreP will be doing internode timer corrections. So it does a ping pong between each node to figure out what the clock offsets are, and then it will be using that for the subsequent measurements. So there's all sorts of measurement overheads which are hidden away here, which are not reported correctly by ScoreP yet.
Fine. So I need to do a timing that doesn't include MPI init and run it with and without ScoreP to basically get that, isolate the MPI init over.
I would not include MPI init thread in any meaningful measurement comparison. And even aside from the ScoreP side of things, MPI init thread is when MPI is initializing buffers and doing all sorts of stuff. It's also, I mean, by that point, it's already distributed your executable across the different nodes, but it's doing a lot of things that are certainly MPI internal and MPI dependent and vary from run to run in non-obvious ways. So I would be very cautious about including MPI init thread, or MPI finalize, which is another critical function. Those are things that, of course, the measurement should have. It's why we're showing them here, but they're not things that I would be keen to include in the measurement, unless, you know, if you're running for hours, of course, the init thread and the finalize are negligible. But here, when we're only running for 40 seconds, the fact that we have 0.12 seconds in the init thread is also negligible, but it's also something that we want to be careful about.
Okay, fine.
As I said, the color coding we're seeing here is one way of guiding the eye to where most of the time is spent, or whatever metric we're looking at. And in this case, we're being drawn to something called iteration. And inside iteration, we have a couple of routines. We have one which is exchange, something about boundary conditions, and something which is ADI, which is a solver that's doing X, Y, Z solves, doing something about computing a right-hand side, and also something else. So there's all sorts of computation going on here. And again, as we zoomed in here, as we drilled into iteration, we're seeing the color coding has changed, and we're seeing that most of the time is in these three X, Y, Z solvers. If I expand the solver, I see inside that there's a parallel region, and inside that parallel region there's a parallel do, and inside the parallel do I see more functions, more application functions. Matrix vector, subtraction, matrix multiplication. I think that's, one's a matrix multiply, one's a matrix vector multiply. So these are actually where a lot of the time is spent, a lot of the computation time is spent. And as I select one of these here, the values on the right-hand side change, so I can see precisely how much time was spent by each of the threads for whatever routine I've selected. And if I was to drill down into the X, Y, and Z solver, I would actually, in this case, see more or less the same functions. They are the same functions, but the timing might have changed, will have changed in various complex ways. So what do we have here? We already saw that we had MPI. That's coming from the MPI library interposition. We're seeing things that are marked as OpenMP parallel regions, OpenMP do, open implicit barrier. Score P instrumented the source code to get that information. And so we can see how much time is in the barrier at the end of the parallel region, or we can see where the parallel region is taking place. And we're also seeing these other functions, and these are the functions from the application. You don't know this application, so you're not necessarily going to recognize these functions, but these are the functions that are part of the application itself. Along with xsolve, along with ADI, along with really important things like timer start and timer clear. So we're combining all of that information, and we've got a tree structure that is allowing us to see how it fits together, and we see which parts are executed on all of the threads and which parts are only executed outside of the parallel regions, and outside the parallel region we only have the master thread executing. Here initialize is being executed with a parallel region, so they're all executing part of it. So while I'm here, I'm going to mention iteration. And iteration isn't part of the application itself. Iteration is, as we were discussing a little bit earlier, an additional marker that Score P has added, or we added to the source code to say that this is where we're really interested in timing here. I can see from the application's timer routines that it's also interested in timing this. So this is the benchmark part of the code execution, is between the start and the stop here, and we've just marked that with iteration so that it's easy for us, easy for me at least, to be able to distinguish this is the interesting benchmark part of the code, as opposed to up here we have the same routines. So this ADI, this exchange QBC, were actually executed as a warm-up before we went into the benchmark iteration here. So that was the benchmark's way of warming up the cache and making sure that the code was in cache, the data was in cache that it would execute with, so that when it came to do the benchmark execution, it wasn't going to suffer from one-off initialization overheads. But it also allows me to see and distinguish this is the execution of the ADI in the initialization, which is not interesting, from the ADI which is executed here in the iteration, which is the part that I'm really interested in because the application was interested in timing that part. I can also see at the end here something which is interesting that's called verify, and it's doing some, the part that's doing the verification after it has timed the benchmark execution. It's verifying that it got the results to the correct tolerance, and for doing that it's having to do some reductions. Where's the other? Oh, yeah, there's different reductions which is doing to collect the values from different processes and then aggregate those together and verify that the solution we got in the benchmark execution is valid. Hopefully your execution also was valid as well. So we didn't need to put this iteration in here, but it helped us to get a little bit more structure into this execution. There's also something up here at the beginning which is telling Score P that part of the execution is not interesting, and so it should turn off measurement for that part. Because measurement is turned off, I can't see what's in there, but it wasn't interesting, and so I turned it off. I could have turned it off for the initialization here as well, but I was happy to keep those. So there are controls that you'll see later that allow you to customize what's in the measurement, what you add, what you remove from it. I'm not going to go through things much more because we want to probably take a break for lunch fairly soon. One of the metrics that's on the left-hand side here is bytes sent and received. I see most of the data is sent and received in this iteration. There's also, of course, some data sent between the processes as part of the reduction. But if I go into the iteration, all of the MPI bytes that are sent and received is in the exchange, it's not in the ADI. So the ADI, where most of the time is spent, is purely computational. At least there's no MPI in there, whereas the bytes sent and received is in this exchange part. And if I expand that, I see here the MPI send. So the bytes are sent on the MPI send, and I see that we have something like, was that about 300 megabytes being sent by each of the master processes. I also see that some of them are sending more than others. So again, that's the nature of the computation here, that some processes have more data to send than others. And if I wanted to see how many sends they do, I go to the visits, and the visits tell me that they're each doing 1400. So they're each sending 1400 messages in this part of the code. But the amount of data that they're sending, the bytes sent, is something that's varying, something that we're seeing is different. If I select the bytes received message, the bytes received metric, I can see that pretty much all of the data that was sent was actually received. There was none went missing. It's also can be considered some sort of sanity check. And if I look to see where the data is received, there's actually no data received in the I receive. The I receive is just providing a buffer so that the data could be received, but it doesn't do any receiving itself. The data is actually received in the all wait in the wait all. And in this case, the amount of data that's received by each process pretty much corresponds to the amount of data that they're sending. That's not necessarily the case. I mean, if I send a lot of data, I might only receive a little bit of data back. But in this case, it's symmetric, that if I send a lot to X, Y, and Z, I expect the same amount of data to be sent back when I from X, Y, and Z when they have that data coming. So I have visits, the number of times something there is executed. I have time, how much time it's taking, and I have the amount of data that's sent and received. But one of the things that we shouldn't really take too much interest in the time is at this point is because we know that there was a lot of measurement overhead. The execution time here was much higher than what we wanted to when or the reference version. I don't remember what it was, but it was about 10 seconds, and now we're up to about 40 seconds of execution time here. So we have quite a lot of measurement overhead, and a lot of that measurement overhead can be traced to these functions here, which have very high visit counts. So each of these routines here has been executed hundreds of thousands of times, tens of thousands of times by each thread, and not only executed a lot here. So if I do if I hold down the control when I'm selecting here, I can get multiple values. And when I have the multiple values selected, then I'm seeing the aggregate value on the right-hand side. All of those in the X and the Y and the Z are all executed tens and hundreds of thousands of times. And maybe that's something we don't really need to know, because if I know the time in the parallel region, that would actually be good enough for me. I want to know the time in the different MPI functions. I want to know the time in the waiting in the barriers in the OpenMP. But I don't really need to know how much time is spent in each of these purely computational routines. And so what we'll see next is that there's a way in which we can say, exclude those from the measurement. And let's see if that's one way of reducing the measurement overhead. Are there any questions while I'm in here looking at COOP? Because otherwise I would finish this and we would then decide what to do next.
So Brian, there was one question about CUDA. How would the system tree change? So would be there additional entries for GPUs in the system trees?
So I'll just load a measurement that includes CUDA, and this was run on the Joule system. It's a nice big measurement with a single MPI process, but of course it could be many processes. We're seeing the OpenMP threads, and we're seeing the CUDA. In the middle, I have the MPI, I have the OpenMP parallel regions, and this was OpenACC. So I see where OpenACC is being used by various parts of the code. Now, it's telling me that there's no time spent in CUDA, and that's because the way in which the tree is structured, the CUDA kernels actually appear separately. They're executed asynchronously from the CPU, and that's why in the call tree we can't really easily associate the kernels with the place where they are created and launched. So that's why we're seeing the launch here, but the actual execution of the kernel, and there's just one kernel in this case, is shown in a separate part of the call tree. And I can see how often those kernels are executed. This is a very complex one, just executed once. And we'll see more about how to break out the time from MPI, so that break out the time so we see the different time in CUDA versus OpenACC and MPI. But this we'll see later. So the right-hand side here is our system tree. It has our threads executing on the cores, and it has CUDA streams executing on the GPUs.
So Brian, do you have any idea of whether the sort of instrumentation overhead is much higher for GPUs? It sounds much harder because they're once removed from, or maybe that makes it less. I don't know. Do you have any experience of that, or general comment?
Well, the CUDA calls are library calls, and we're just capturing those. So if you have, well, I mean, the CUDA overheads are the library calls executing the kernels. The fact that we are capturing them and measuring them and timing them is an additional overhead, but it's typically not a big overhead compared with the actual kernel execution cost itself.
Okay, it's just there were so many CUDA threads as well. I wonder if that caused you an issue, but maybe that's I guess you can deal with tens of thousands of MPI processes, so maybe that's not a big deal.
In this case, we're seeing that each of the OpenACC kernels is executing as a different CUDA stream, and that's why we're showing 8 different CUDA streams here. I need to go back to something a bit more meaningful. Well, this was just a simple toy example to show the principle, but
yeah, no.
I mean, you may have hundreds of thousands of CUDA streams, you may have certainly hundreds of thousands of kernels. All of those can be additional overheads because we have to, every time a kernel is executed, we are timing, we will be storing those events in a buffer on the GPU, and then when the CUDA kernel finishes, or when there's a synchronization point, that's the point when we would capture what the GPU is doing and transfer it to the profile or to the trace buffer.
Apologies if you already mentioned this, but you said this was OpenACC. Can you do OpenMP as well? Or?
This is OpenMP, this is OpenACC. We do not yet handle OpenACC target offload, if that's the question.
Oh, so that's what I meant. Sorry, I should be more. Okay. Fine.
Yeah. So we're getting the OpenMP part that's executing on the CPU. We're not able to get the OpenMP target offload. We will see the CUDA kernels that OpenMP target offload will typically generate a CUDA kernel, and we can capture those. But without the target offload, we are missing a piece there.
Okay, so you'll get lower level information. It might be a bit harder to interpret how it relates to your actual source code because you don't currently have that glue right
here we're seeing CUDA as a kind of orthogonal level of information to the OpenACC. If there were explicit CUDA calls, and I don't think there are any in this code, those explicit CUDA calls, we would see those. I'm not seeing. So here are the CUDA calls which are inside the MPI init. Maybe those are interesting, maybe they're not interesting. But this is where it's setting up the GPU to GPU ability to do MPI transfers, so GPU direct. So GPU aware, this is a GPU aware MPI, which means that the MPI data is transferred directly between the GPUs without needing to be initially copied to the CPU and then from the CPU to CPU and then back down to the GPU on the other side. So this is GPU aware, and that's why the CUDA calls are inside the MPI init. But we're getting into a lot of GPU specific information that's probably not going to help people in Archer.
So maybe just briefly, so in the future version of SCORP, we are going to support OpenMP target via the OMPT tools interface, but this will take some time. So but we are working on this. And Brian, you already stopped sharing. There was a question about the Sunburst tab, and I don't remember if you showed the statistic tabs as well. So in the system.
There's lots more tabs that you can explore, and we'll come back to some of them later. But
Okay.
I'm conscious that we're already into the lunch break, or at least what was planned as the lunch break. So that's why I'm wondering. I think we want to give people an hour for lunch, and we can continue the presentation after lunch.
I think we probably should break, because I appreciate some people like you will be an hour ahead as well. So it's already getting on a bit.
I already grabbed my lunch when we were in the break, but because I couldn't wait. But I want to give other people a chance, and then so I would say we start again at in an hour's time, which is quarter to, I don't know, quarter to the next hour, whatever you are. Does that sound reasonable?
Yeah, that sounds good. I just say to people that, you know, obviously Brian and Christian have you know, great slides and nicely pre-packaged examples, but you know, the majority of the afternoon I think is being reserved for sort of one-on-one advice. So that, you know, that's where you can hope to get the most benefit from. You know, try it out on your own codes, and then you can get, you know, one specific advice on your own codes. That's the, you know, how to get Scalasca working for your own codes. But yeah, that's great. So we'll come back in just over an hour at 13:45 British Summer Time. I'll put okay. I'll maybe put a whiteboard. I'll maybe put that note on the screen just so everyone can see it. So.
The session again. Are you going to stop recording? I guess, but you'll keep the session open.
Yes, yeah, I think we normally, just to keep the files, we'll stop recording now, I guess. I saw that Claire just joined, actually, maybe that's her. But we'll just stop the recording now and then. But yeah, the session, in fact, it's the way that
we normally stop it and immediately restart it, and that way we don't run the risk of forgetting to restart it, and I just trim out the null space when I'm doing the processing.
The way Claire set it up, I'm pretty sure that it's actually the same. The session's the same this afternoon, but the link works tomorrow, doesn't it, Claire? The Collaborate link.
Right the way through. Yep.
Fine. The only thing you have to manage is the reservation.
People can disconnect if they want, or they can just stay connected. And Christian or I will probably be still around if you have some questions. At least, as I said, I've had lunch, so I'll be watching the chat or listening for any questions. Although I can't actually show this screen and listen for questions at the same time. So start sharing. Maybe I wasn't sharing.
Yes, just a short question. I just missed one point. So if you have OpenMP target, this will also this OpenMP offloading will also show up, right? In the
No, not yet. So we are working
on
OMP target. So if the underlying hardware is NVIDIA GPU, then we can capture something using the CUPT interface from NVIDIA, but so the OMPT target or the tools interface that we are working on this. So and on all runtimes supported right now. So.